Central limit theorem. Lesson objective: solve problems using the central limit theorem. Before we jump into the problems, let's review the sampling distribution of x bar. A sampling distribution is the probability distribution of a sample statistic that is formed when samples of size n, that's our sample size, are repeatedly taken from a population. So here's a visual. We have this population and we take random samples of the same size n from a population, and we do this over and over and over again. If the sample statistic is the sample mean, then the distribution is the sampling distribution of the sample means. Now what that means is each sample is going to have a sample mean, and each sample mean is now going to be a data value in this sampling distribution. So what kind of distribution is this new sampling distribution going to have? Well, we always want to talk about the shape, the center, and the spread for a distribution. So if the sample size is 30 or more, that's a rule of thumb, and that sample is taken from a population with any type of distribution. It can be skewed left, it can be skewed right, it doesn't matter, with a mean mu and a standard deviation sigma. So here we have two different cases, two different populations. It turns out that the sample means will have a normal distribution. So the shape will be bell-shaped, symmetric, with one mound. If the population is normal with mean mu and standard deviation sigma, then the sample size does not matter. Any sample size will produce a distribution of sample means that is normal for any size n. So we know the shape. The shape is going to be normal if the sample size is 30 or more and we don't know anything about the population, or sample size doesn't matter. The sampling distribution of the sample means will still be normal if we know that the original population is normal. So let's talk about the center. The center, it turns out that the mean of all the little sample means, if we average all the x bars, it is equal to the population mean mu. So the mean of the sample means is equal to the population mean. For the spread, the sampling distribution is always going to be smaller. And how much smaller? Well, that depends upon the sample size. The standard deviation of this sampling distribution, and this is the notation, is equal to sigma, the population standard deviation, divided by the square root of the sample size n. This is known as the standard error, and it is the standard deviation of the sampling means. So let's do some problems. The duration of human pregnancies can be described by a normal distribution with a mean of 266 days and a standard deviation of 16 days. What percent of pregnancies should last between 250 and 280 days? Okay, we have our distribution. It's a normal distribution, so the shape is symmetric with one mound. The center is described by the mean, it's 266, and the spread would be measured by the standard deviation, which is 16 days. Now this question is asking what percent, so we're going to find the probability, but we do not need to employ the central limit theorem here, is because we're not talking about a distribution of sample means. This is just using a normal distribution and finding a probability. So how do we answer this? Well, of course, we first want to draw a picture. We want to find the area in between these two x values, 250 and 280. So we need to convert these x values to z-scores. So for the first z-score, that would be our x, 250, minus the mean, 266, divided by 16. And if we round that to two decimal places, we always round z-scores to two decimal places, we get -1. So that z-score that corresponds to this value is a -1. For the second z-score, it's 280 minus the mean divided by the standard deviation, and we get a positive 0.88. So we need to find the area in between these two z-scores. So using table 5, we look up the largest z-score, write that area down, then look up the smallest z-score, write that area down, and subtract the two. You should get 0.8106 minus 0.1587, and that gives us a probability of 0.6519. So the percentage would be about 65% of pregnancies last between 250 and 280 days. B, at least how many days should the longest 10% of all pregnancies last? So this is a problem where we're working backwards. We're not finding a probability, a percentage, an area. We are finding how many days. We are finding an X. This has the same units as the mean and standard deviation. So this is finding the value of X. So how do we do that? Well, the longest 10% is telling us an area. That is the 90th percentile. So if we draw a picture, clearly we can see that the z that corresponds to this x value is going to be positive because it's above the mean. And if this is 10%, then that means the area to the left is the complement of that, which is 90%. So in table 5, in the body of the table, we want to find the closest z-score that comes to 0.90 or 90%. That turns out to be a z-score of 1.28. So now we know the z, we want to find the x. So using this formula, x equals mu plus z times sigma, substituting what we know, 266 for the mean, 1.28 for the z, times our standard deviation is 16, gives us 286.48 days. So about 287 days is the number of days that would separate the bottom 90% of pregnancies from the top 10%. So only about 10% of pregnancies are going to be longer than this 286.5 days. Part C. Suppose an obstetrician is currently providing prenatal care to 60 pregnant women. Let x bar represent the mean length of their pregnancies. According to the central limit theorem, what is the sampling distribution of the sample mean? Because we are asked to discuss a group of 60 pregnant women, now we're going to employ the central limit theorem. Our sample size is 60, and we want to look at this distribution of the sample means where each sample of 60 would produce an x bar, and if we looked at all those possible x bars, what would the distribution of the sample means look like? Well, it's going to have a shape, center, and spread. Because the sample size 60 is bigger than 30, our rule of thumb, the central limit theorem states that the shape will be normal, and it will have the mean equal to the population mean, which is 266 days, and that sort of makes sense. And the standard deviation, which we call the standard error, is going to be smaller. It's going to be 16 divided by the square root of the sample size, which is 60. And that turns out to be about 2.0656. And again, this is always going to be smaller than the population standard deviation. Part D. What is the probability that the mean duration of these patient pregnancies will be at most 270 days? Okay, we are wanting to find the probability of these sample means with size 60. So we're going to use the mean of the population, 266, and the standard error to produce the z-score. So let's draw a picture. So our mean is at 266. We want 270 and less. We know it's less because it says at most. That means area to the left. So we need to convert 270 to a z-score. So that is going to be 4 divided by our standard error, and then we round it to 2 decimal places, and you should get 1.94. So this is about 2 standard deviations above the mean. So looking up the area to the left of z equals 1.94, we get a probability of 0.9738. Part E. What is the probability that the mean duration of these patients' pregnancies will be at least 39 weeks or 273 days? Well, at least is area to the right. So if we draw a picture, we want to the right of 273 days. Now that is going to be a very small number. Using our z-score, we are going to get 7 divided by a standard error. And again, we're using standard error here because we are using the standard deviation of the sample means. It's going to be smaller than the population standard deviation. And rounding this to 2 decimal places, we get 3.39. So this is more than 3 standard deviations above the mean. Because we want area to the right, we have to do 1 minus what's in the table. So it's 1 minus 0.9997, which gives us an area 0.0003. That's why it's hard to see the area colored in the picture, because the probability is very small. Thanks for watching.